Tonight, we're going to explore one of the most extraordinary capabilities that telescopes give us. When you point a telescope at the sky, you're not seeing the universe as it is right now. You're seeing history unfold. Not in the science fiction sense, but in a very real, very literal way. By the end of tonight, you'll understand exactly how this works, why it matters, and how it's changed everything we know about the cosmos. Before we begin, if this kind of exploration interests you, hitting like or subscribe really helps the channel. It's quick for you, but makes a huge difference for me. Now, let's jump in. When Galileo first pointed his telescope at the night sky in 1609, he had no idea he was looking into the past. He saw mountains on the moon, spots on the sun, moons orbiting Jupiter, and countless stars invisible to the naked eye. These discoveries revolutionized our understanding of the solar system. But Galileo didn't realize that every photon entering his telescope had been traveling through space before reaching him. It wasn't until the late 1600s that astronomers began to understand that light has a finite speed. Ole Rømer, a Danish astronomer, was studying the moons of Jupiter in 1676 when he noticed something odd. The times when Jupiter's moons disappeared behind the planet varied depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther away, they happened later. Rømer realized this delay was caused by light taking longer to cross the greater distance. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation wasn't quite right because he didn't know the exact size of Earth's orbit, but he proved something fundamental. Light doesn't travel instantly. This discovery transformed how we think about observation itself. Light travels at about 300,000 kilometers per second or 186,000 miles per second. That's incredibly fast by human standards. But space is so vast that even at this speed, light takes time to travel from distant objects to our instruments. Point a telescope at the moon, and the light you're collecting left its surface 1.3 seconds ago. Point it at Jupiter, and depending on where both planets are in their orbits, you're gathering photons that departed 35 to 50 minutes earlier. Aim at Sirius, the brightest star in the night sky, and you're capturing light from 8.6 years in the past. Look at the Andromeda galaxy through any telescope, from a backyard instrument to Hubble, and every photon has been traveling for 2.5 million years. The farther away an object is, the older the light we receive from it. This creates a natural timeline across the universe. Nearby objects show us recent history. Distant objects reveal ancient history. And by building better instruments that can detect fainter light, we push deeper into the past. Every telescope ever built, from Galileo's simple refractor to the most advanced space observatories, works on the same principle. They collect light, focus it, and let us see things too faint or too distant for our naked eyes. To appreciate how telescopes work, we need to understand what happens to light during its journey across cosmic distances. Light isn't just moving through empty space. It's navigating a universe that's expanding, passing through dust and gas, and experiencing the effects of gravity. When a photon leaves a distant star, it begins a journey that might last thousands, millions, or billions of years. During that journey, the photon maintains its energy and direction unless something interferes with it. This remarkable stability is what makes astronomy possible. If photons degraded or changed properties randomly during their travels, we couldn't reliably interpret what we see. But the universe does affect light in specific, predictable ways. The expansion of space stretches the wavelength of photons traveling across cosmological distances. This redshift is directly proportional to distance. Telescopes measure this redshift through spectroscopy, breaking light into its component wavelengths and measuring how much familiar spectral lines have shifted toward longer wavelengths. This redshift tells us not just how far away an object is, but how long ago the light was emitted. Dust in space also affects light traveling to our telescopes. Interstellar dust grains, typically smaller than smoke particles, scatter and absorb light. Blue light scatters more than red light, which is why distant objects often appear redder than they actually are. Telescopes must account for this reddening to determine an object's true properties. By observing at multiple wavelengths, from ultraviolet through visible to infrared, telescopes can see through dust and reconstruct what an object looked like when the light left it. Gravitational fields bend light, a phenomenon Einstein predicted in his general theory of relativity. When light passes near a massive object like a galaxy cluster, its path curves. Telescopes observe this gravitational lensing in dramatic ways. Background galaxies appear distorted into arcs or even multiple images. By analyzing these distortions, astronomers map the distribution of mass, including dark matter, in the foreground lensing object. Some photons travel relatively unimpeded from their source to our telescopes. Others take scenic routes, deflected by gravity, scattered by dust, or delayed by passing through varying densities of intergalactic gas. Each photon carries information not just about its source, but about everything it encountered along the way. The atmosphere presents challenges for ground-based telescopes. Air turbulence causes starlight to twinkle and smear. Water vapor absorbs certain wavelengths. Light pollution from human sources contaminates the darkness telescopes need. This is why some of the most powerful observatories are space telescopes operating above the atmosphere with minimal interference. Modern telescopes have become increasingly sophisticated at gathering photons from objects so distant and faint that only a trickle of light reaches us across billions of years of travel. The size of a telescope's primary mirror, or lens, determines how much light it can collect. Light-gathering power increases with the square of the diameter. A telescope with a 4-meter mirror collects 4 times as much light as a 2-meter telescope, not twice as much. This relationship drives the construction of ever larger telescopes. More light means detecting fainter objects, which usually means more distant objects. But building large mirrors is extraordinarily difficult. Glass sags under its own weight. Temperature changes cause expansion and contraction. Traditional solid mirrors become impractical beyond about 8 meters in diameter. Engineers have developed segmented mirror designs where dozens of hexagonal segments work together as a single optical surface. The James Webb Space Telescope uses 18 hexagonal beryllium mirrors, each 1.3 meters across, forming a combined 6.5-meter mirror. The extremely large telescope under construction in Chile will have a 39-meter segmented primary mirror consisting of 798 individual hexagonal segments. Each segment must be precisely positioned and angled to within nanometers. Active optics systems constantly adjust these segments to maintain perfect optical shape despite wind, temperature changes, and the telescope's changing orientation. Ground-based telescopes face Earth's atmosphere as an obstacle. Air turbulence causes stars to twinkle and smear. Adaptive optics systems revolutionized ground-based astronomy by compensating for this in real time. A guide star, either natural or created by a laser beam, provides a reference point. Sensors measure how the atmosphere distorts this reference light. A deformable mirror, adjusted hundreds or thousands of times per second, corrects the distortion. The Keck telescopes in Hawaii each have mirrors 10 meters or 33 feet across. The Very Large Telescope in Chile consists of 4 8.2-meter telescopes that can work together. These instruments can see incredibly distant objects. This technology allows ground-based telescopes to achieve resolution comparable to space telescopes, despite observing through Earth's turbulent atmosphere. Detector technology has advanced just as dramatically as mirror design. Early telescopes relied on the human eye, which is remarkably sensitive but limited. Photographic plates replaced eyes, allowing long exposures that accumulated faint light over hours. But photographic plates capture only about 1% of incoming photons. Modern electronic detectors can capture 90% or more of incoming photons. These detectors count individual photons. When a photon from a galaxy 10 billion light-years away strikes the detector, it liberates an electron that gets counted and recorded. That single photon has been traveling for 10 billion years. Millions of such photons, accumulated over hours of exposure, build up an image. Spectroscopy requires specialized equipment that spreads light into its component wavelengths. Gratings or prisms separate light by wavelength, creating a spectrum. By analyzing absorption and emission lines in these spectra, astronomers determine an object's composition, temperature, velocity, and distance. This information comes from light that might be thousands or millions of years old, encoded in the specific wavelengths present or absent. Temperature matters critically for infrared telescopes. Everything emits infrared radiation based on its temperature. To detect faint infrared light from distant objects, telescopes must be much cooler than their targets. The Spitzer Space Telescope used liquid helium to cool its instruments to just a few degrees above absolute zero. When the helium ran out after 5 years, Spitzer could no longer observe at the longest infrared wavelengths, though it continued operating at shorter wavelengths where cooling requirements were less stringent. Webb, launched in December 2021, operates at temperatures around 40 degrees above absolute zero, shielded from the sun's heat by a 5-layer sunshield the size of a tennis court. This extreme cooling allows it to detect the faint infrared glow from galaxies over 13.5 billion light-years away. Webb observes primarily in infrared light, crucial because the universe's expansion stretches light from distant galaxies to longer wavelengths. What left as ultraviolet or visible light arrives as infrared after traveling 13 billion years. The Hubble Space Telescope, launched in 1990, orbits above Earth's distorting atmosphere. It can see fainter, more distant objects than any ground-based telescope of its era. When Hubble pointed at what appeared to be empty patches of sky and stared for days gathering light, it revealed thousands of galaxies. The Hubble Ultra-Deep Field, created by observing a single tiny patch of sky for over 11 days of total exposure, revealed galaxies from over 13 billion years ago. Data processing has become as important as the telescopes themselves. A single deep exposure from Hubble or Webb might contain hundreds of galaxies, each requiring analysis. Software identifies objects, measures their properties, and catalogs them. Machine learning algorithms now assist in this process, trained to recognize galaxies, stars, and other objects automatically. These tools let astronomers sift through vast amounts of data, extracting information about the past from millions of photons. Interferometry takes telescope technology in a different direction. Instead of building one enormous mirror, interferometric arrays combine light from multiple smaller telescopes. The Very Large Telescope Interferometer can link 4 8.2-meter telescopes plus 4 smaller auxiliary telescopes, achieving resolving power equivalent to a telescope over 100 meters across. This technique works by precisely measuring and combining the phase of light waves arriving at different telescopes. Radio interferometry has achieved even more impressive results. The Event Horizon Telescope linked radio dishes around the world, creating an Earth-sized virtual telescope. This array produced the first images of black hole event horizons, resolving features that would require an optical telescope the size of our planet. Time-domain astronomy requires telescopes that can rapidly survey large areas of sky, comparing images taken hours, days, or weeks apart. The Zwicky Transient Facility in California photographs the entire visible sky every 2 days, identifying anything that's changed. When it detects a new supernova, other telescopes worldwide quickly observe it in detail. This coordination allows astronomers to study stellar explosions from multiple viewpoints, gathering light that left those stars hundreds, thousands, or millions of years ago. For optical and infrared telescopes observing electromagnetic radiation, there's a fundamental limit to how far back they can see. The ultimate barrier is the cosmic microwave background. This faint glow fills the entire sky, coming from every direction. It's the oldest light in the universe, released about 390,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before this moment, the universe was opaque. It was too hot for atoms to exist. Electrons and nuclei floated freely as a plasma, and photons couldn't travel far without scattering off electrons. The universe was like a dense fog, where light couldn't propagate freely. Then, about 390,000 years after the Big Bang, the temperature dropped below about 3,000 degrees. Electrons combined with nuclei to form neutral atoms. Suddenly, light could travel freely. The universe became transparent. This light has been traveling ever since, stretched by the universe's expansion from visible light to microwave wavelengths. Radio telescopes can detect this cosmic microwave background. Satellites like COBE, WMAP, and Planck have mapped it in exquisite detail. But we can't see beyond it with electromagnetic radiation. Before recombination, the universe was opaque. Any light from that era scattered and never traveled freely to us. This means optical and infrared telescopes have a fundamental horizon at about 13.8 billion years in the past. That's the age of the universe. You can't see older than that because nothing existed before then. But telescopes can approach this limit. Webb is detecting galaxies from only 200 to 300 million years after the Big Bang. Future telescopes might push even closer, finding some of the very first galaxies that ever formed. What about other types of telescopes? Neutrino telescopes might eventually detect the cosmic neutrino background, which formed even earlier, about 1 second after the Big Bang. Gravitational wave detectors might someday observe primordial gravitational waves from even earlier times. But these wouldn't be traditional telescopes. They'd be different types of detectors sensitive to different messengers from the early universe. For now, electromagnetic telescopes, from radio to gamma ray, all face the same barrier. Everything before recombination is hidden behind the opaque early universe. Within about 1,000 light-years of Earth, powerful telescopes can detect roughly 100,000 stars. Every observation captures light from years, decades, or centuries ago, revealing stellar physics frozen in time. Sirius is a binary system. The bright star, Sirius A, is about twice the Sun's mass. Its companion, Sirius B, is a white dwarf, the collapsed core of a star that exhausted its fuel. White dwarfs are remarkable objects, about the size of Earth but containing roughly the mass of the Sun. In 1862, Alvin Graham Clark tested a new telescope by observing Sirius and discovered the faint companion previously hidden by Sirius A's glare. Betelgeuse, the red supergiant in Orion, is visible to the naked eye as a bright orange star. But telescopes reveal its massive size, its irregular surface pulsations, and its surrounding nebula of ejected material. This massive star will explode as a supernova sometime in the next 100,000 years. When it does, it will briefly become as bright as the full moon, visible even during the day. But it might have already exploded. The explosion could have happened in the year 1500, or any time in the past 5.5 centuries. We wouldn't know yet. Larger telescopes reveal fainter, more distant stars. The red giant Arcturus, about 37 light-years away, is easily visible in modest telescopes. For someone observing Arcturus in 2025, they're gathering photons that departed in 1988. The Hubble Space Telescope has photographed many stars in incredible detail. It resolved the surface of Betelgeuse, showing bright spots and dark regions. It captured the Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054. The Crab is about 6,500 light-years away, so the explosion actually happened around 4550 BC. Hubble's images show an expanding shell of gas with a pulsar, a rapidly spinning neutron star, at the center. Ground-based telescopes, equipped with adaptive optics, can also achieve remarkable detail. The Very Large Telescope Interferometer can combine light from multiple telescopes, effectively creating a telescope hundreds of meters across. This technique has resolved the surfaces of several red giant stars, showing how they pulsate and change over time. The Gaia Space Telescope, launched in 2013, has revolutionized our understanding of nearby stars by precisely measuring their positions, distances, and motions. Gaia has mapped over 1 billion stars. By comparing positions over time, Gaia tracks how stars move through space. This motion matters because stars don't stay in one place. They orbit the galactic center, taking hundreds of millions of years to complete one orbit. They also have peculiar motions, moving relative to their neighbors. Variable stars provide another window into stellar physics. Cepheid variables pulsate regularly, growing brighter and dimmer over periods of days to months. Henrietta Leavitt discovered in 1912 that the period of pulsation is directly related to the star's intrinsic luminosity. This relationship turned Cepheids into cosmic distance markers. The period luminosity relationship works because more luminous Cepheids have larger atmospheres that take longer to pulsate. By measuring a Cepheid's period, astronomers determine its intrinsic brightness. Comparing intrinsic brightness to apparent brightness reveals distance. This method, refined over decades, underpinned Hubble's discovery of cosmic expansion and remains crucial for calibrating the cosmic distance ladder. Other variable stars follow different patterns. RR Lyrae stars, common in globular clusters, pulsate over hours. Mira variables, red giants nearing the ends of their lives, vary over months with amplitudes of several magnitudes. Each type reveals different physics and provides different tools for understanding stellar evolution. By combining observations over decades or centuries, astronomers watch how these pulsations change. Are they perfectly regular? Do they drift slowly? These questions require long observational baselines. Telescopes capture data now. Historical observations from decades or centuries ago provide comparison. Together, they reveal slow changes happening over periods longer than human lifetimes. The stars we observe exist within neighborhoods, gravitationally bound systems that evolve over millions of years. By studying these stellar communities at various distances, telescopes reveal how stellar populations change and develop. Star clusters are laboratories for understanding stellar evolution. Open clusters contain hundreds to thousands of young stars born from the same molecular cloud. The Pleiades, visible to the naked eye but spectacular through telescopes, is about 440 light-years away. The Pleiades stars are all roughly 100 million years old. They're still surrounded by wispy nebulosity, remnants of the cloud from which they formed. Telescopes reveal hot, blue, massive stars that will burn out in a few 100 million years, along with cooler, longer-lived stars that will shine for billions of years. Globular clusters present a stark contrast. These spherical collections of hundreds of thousands to millions of stars orbit in the halos of galaxies. Messier 13, the great globular cluster in Hercules, sits about 22,000 light-years away. The stars in Messier 13 are ancient, over 12 billion years old. They formed when the universe was young, before the Milky Way's disk assembled. These stars contain very few heavy elements because they formed before many generations of stars had enriched the cosmos with elements beyond hydrogen and helium. Stellar associations are looser groupings than clusters. The Orion OB1 association, spread across the constellation Orion, contains young, hot, massive stars. These associations are transient, dispersing over tens of millions of years as member stars drift apart. Within these associations, telescopes reveal ongoing star formation. The Orion Nebula, a glowing cloud of gas illuminated by young stars, is giving birth to new stars. Infrared telescopes peer through the dust to see protostars still forming, embedded in dense cocoons. Binary and multiple star systems add complexity to stellar neighborhoods. About half of all stars exist in binary or higher-order systems. Telescopes reveal these companions through various methods. Directly imaging both stars, detecting periodic wobbles in a star's motion, or observing eclipses as one star passes in front of another. Algol, the demon star in Perseus, is an eclipsing binary about 93 light-years away. Every 2.87 days, a dimmer, larger star passes in front of the brighter companion, causing Algol to fade noticeably. These eclipses have been observed for centuries. Some binary systems interact dramatically. When one star evolves into a red giant and expands, its outer layers can be pulled onto its companion. These interacting binaries produce novae, sudden brightenings when accumulated hydrogen on the companion star ignites in runaway fusion. Stellar streams represent the remnants of disrupted clusters. The Hyades, about 150 light-years away, is gradually dispersing. Telescopes tracking individual member stars reveal how the cluster is being pulled apart by the Milky Way's tidal forces. Moving groups share common motion through space, evidence of a shared origin. The Ursa Major moving group includes 5 of the Big Dipper's 7 stars, all moving in the same direction. These stars formed together about 300 million years ago and have been drifting apart ever since. High-velocity stars streak through the galaxy at speeds exceeding 600 kilometers per second or 370 miles per second. These stellar outcasts were likely ejected from binary systems when their companions exploded as supernovae. Telescopes tracking high-velocity stars see their motions from years or decades ago, allowing astronomers to trace their orbits backward to find their origins. Brown dwarfs occupy the boundary between stars and planets. Too small to sustain hydrogen fusion, they glow dimly from residual heat. Telescopes have detected hundreds of brown dwarfs within a few dozen light-years. These failed stars help astronomers understand the lower mass limit for star formation and the transition between stellar and planetary objects. The structure and behavior of stellar neighborhoods change based on their location within galaxies. Stars near galactic centers experience different environments than those in spiral arms or the galactic halo. Telescopes, studying stars at various galactic locations, reveal these environmental effects. In the dense galactic center, stars orbit tightly packed around the central supermassive black hole. The closest stars complete orbits in just years or decades. Telescopes have tracked individual stars orbiting Sagittarius A star, the Milky Way's central black hole, revealing the black hole's mass through precise orbital measurements. These observations capture stellar motions from about 26,000 years ago, the light travel time to the galactic center. Star-forming regions in spiral arms show vigorous stellar birth. Dense molecular clouds collapse under gravity, fragmenting into hundreds or thousands of protostars. The Carina Nebula, about 7,500 light-years away, hosts massive star formation. Telescopes reveal pillars of gas sculpted by stellar winds and radiation, similar to the famous Pillars of Creation in the Eagle Nebula, but even larger. We observed this stellar factory from about 7,500 years ago. The Tarantula Nebula in the Large Magellanic Cloud, about 160,000 light-years distant, contains some of the most massive stars known. R136, a 1, the most luminous star yet discovered, shines with the power of millions of suns. This monster star will live only a few million years before exploding spectacularly. We observe it from 160,000 years ago. Reflection nebulae show how starlight interacts with surrounding dust. Unlike emission nebulae that glow from ionized gas, reflection nebulae simply scatter starlight. The blue color characteristic of reflection nebulae results from the same scattering process that makes Earth's sky blue. The Pleiades reflection nebula demonstrates this beautifully. The young hot stars illuminate surrounding dust, creating a ghostly blue glow visible through telescopes. Dark nebulae represent the opposite, dense clouds that block background light. The Coalsack Nebula, visible to the naked eye as a dark patch against the Milky Way, is about 600 light-years away. Telescopes observing at infrared wavelengths can peer into these dark clouds, revealing protostars forming within. These observations show star formation in its earliest stages, hidden from optical view. Superbubbles form when multiple supernovae explode in close succession within stellar associations. The combined blast waves sweep up surrounding gas, creating enormous cavities hundreds of light-years across. NGC 604, about 11 million light-years away in a nearby irregular galaxy, shows a superbubble clearly. Telescopes detect the hot gas within the bubble and the compressed shell surrounding it. Runaway stars, ejected from their birthplaces by gravitational interactions or supernova kicks, create bow shocks as they plow through the interstellar medium at high speeds. Zeta Ophiuchi, about 440 light-years away, is a massive star racing through space at about 85,000 kilometers per hour or 53,000 miles per hour. Telescopes detect the bow shock ahead of the star, glowing in infrared from compressed gas. Supernova 1987A stands out as one of modern astronomy's most important stellar explosions. On February 23, 1987, astronomers observed a star explode in the Large Magellanic Cloud, a small satellite galaxy about 168,000 light-years away. The explosion itself occurred far earlier. The light had been traveling since the Stone Age. Before the explosion, astronomers had photographed that region many times. After detection, they checked archived images and found the progenitor star, called Sanduleak -69°202, a blue supergiant. This was the first time astronomers definitively identified which specific star had exploded. Hubble continued watching the aftermath. The explosion created an expanding shell of gas visible in multiple observations over the years. Eta Carinae tells another dramatic story. This massive star, about 7,500 light-years away, underwent a huge eruption in the 1840s. For a brief time, it became one of the brightest stars visible from Earth. The eruption created a bipolar nebula called the homunculus. Modern telescopes, especially Hubble, have revealed incredible detail in this structure. The Crab Nebula was first observed by Chinese astronomers in 1054. They recorded a guest star that appeared in the sky, bright enough to be visible during the day for weeks. This supernova explosion occurred about 6,500 light-years away. Modern telescopes reveal the expanding remnant in exquisite detail. X-ray telescopes show hot gas. Optical telescopes show filaments where the blast wave is encountering interstellar material. Radio telescopes detect synchrotron radiation from electrons spiraling in magnetic fields. At the center, all telescopes detect a pulsar spinning 30 times per second. By comparing pulse timing over years, astronomers have detected that the pulsar is gradually slowing down as it loses energy. This slowdown is tiny, less than a microsecond per year, but it's measurable with sensitive radio telescopes. Light echoes provide another way telescopes reveal stellar history. When a star suddenly brightens, light spreads outward in all directions. Some of this light hits dust clouds surrounding the star and reflects toward us. Because the reflected light travels a longer path, it arrives later than direct light. Telescopes can observe these light echoes months or years after the original event. Tycho's supernova in 1572 and Kepler's supernova in 1604 both produced light echoes that modern telescopes have detected. By finding dust clouds that reflected light from these 400-year-old explosions and observing them now, telescopes let astronomers study supernovae from the 16th and 17th centuries in detail impossible at the time. By taking spectra of the light echoes, astronomers determine what type of supernovae these were, improving understanding of stellar explosions across cosmic history. Variable stars of many types have been observed for over a century. Delta Cephei has been monitored since the late 1700s. Mira has been observed for over 400 years. These long observational baselines, captured by generations of telescopes, reveal slow changes over periods longer than human lifetimes. Telescopes reveal not just stars living and dying, but how stellar death enriches the cosmos for future generations. This cosmic recycling demonstrates how stars are connected across time. Planetary nebulae mark the deaths of sun-like stars. Despite their name, they have nothing to do with planets. Early telescopes saw these glowing shells as disc-shaped objects resembling planets, but higher resolution revealed their true nature: expanding shells of gas ejected by dying stars. The Ring Nebula in Lyra, about 2,300 light-years away, is one of the most observed planetary nebulae. The central white dwarf, the exposed core of the original star, illuminates the expanding shell with ultraviolet radiation, making it glow. The Helix Nebula, one of the nearest planetary nebulae at about 650 light-years, reveals intricate structure, cometary knots of dense gas, multiple overlapping shells from separate ejection events, and a hot white dwarf at the center. This complexity tells us that stellar death isn't a simple process, but involves multiple episodes of mass loss spanning thousands of years. Some planetary nebulae show bipolar structures with two lobes extending in opposite directions. The Butterfly Nebula, about 3,800 light-years away, displays this morphology beautifully. The bipolar shape likely results from a binary companion or rapidly rotating star channeling the ejected gas into jets. Supernova remnants provide even more dramatic evidence of stellar death. These expanding shells of debris mark where massive stars exploded. Cassiopeia A, about 11,000 light-years away, is the remnant of a supernova that exploded millennia ago. Telescopes show this young remnant expanding at thousands of kilometers per second, enriching the interstellar medium with heavy elements forged in the explosion. The Vela supernova remnant, much older and closer at about 800 light-years, has expanded to cover dozens of degrees of sky. Radio and X-ray telescopes detect shells and filaments, showing how the blast wave interacts with surrounding gas. At the center, a pulsar spins 11 times per second, the collapsed core of the exploded star. Wolf-Rayet stars are massive stars nearing the ends of their lives. These stellar monsters shed mass at prodigious rates, driving powerful stellar winds that form nebulae around them. WR-104, about 6,000 light-years away, has created a wind-blown bubble in the interstellar medium. Some Wolf-Rayet stars exist in binary systems. When the Wolf-Rayet star's wind collides with wind from its companion, telescopes observe beautiful pinwheel nebulae. Luminous blue variables represent another late stage of massive stellar evolution. These unstable stars undergo irregular eruptions, ejecting significant mass. P Cygni, about 6,000 light-years away, has created a circumstellar nebula from past eruptions. The role of stellar death in cosmic evolution cannot be overstated. Every element heavier than helium was created in stars or their explosive deaths. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stars that died before our sun formed. Watching planetary nebulae and supernova remnants from thousands of years ago shows us this enrichment process in action. Stellar birth is intimately connected to stellar death. Shockwaves from supernovae compress nearby gas clouds, triggering collapse and star formation. The star-forming region around the Cygnus Loop supernova remnant, about 2,400 light-years away, shows evidence of triggered star formation. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. When Hubble photographs it in detail, resolving individual stars, each photon captured has been traveling since early humans were just beginning to use stone tools. Andromeda contains about 1 trillion stars. Some of those stars have probably died since then. New ones have formed. The spiral arms have rotated slightly. Messier 33, the Triangulum Galaxy, sits about 3 million light-years away. Ground-based telescopes can see it as a faint smudge. Larger telescopes reveal its spiral structure. Space telescopes like Hubble resolve individual stars and star-forming regions. The Sombrero Galaxy, famous for its edge-on view, is about 29 million light-years away. Telescopes show a bright central bulge surrounded by a dark dust lane. The Whirlpool Galaxy, about 23 million light-years away, is a favorite target for amateur and professional telescopes alike. Its face-on spiral structure is clearly visible even in modest instruments. Larger telescopes reveal incredible detail in the spiral arms, with bright pink regions marking star-forming nebulae and dark dust lanes outlining the spiral pattern. The Virgo cluster contains over 1,000 galaxies about 53 million light-years away. Telescopes survey this cluster, photographing dozens of galaxies in a single field of view. Centaurus A, about 13 million light-years away, is a peculiar galaxy showing signs of a merger. Telescopes reveal a dark dust lane cutting across an elliptical galaxy. Radio telescopes detect enormous lobes extending far beyond the visible galaxy. Messier 82, about 12 million light-years away, is undergoing a starburst, forming stars at about 10 times the Milky Way's rate. Telescopes detect intense infrared emission from dust heated by young stars. X-ray telescopes show hot gas being driven out of the galaxy by stellar winds and supernovae. Hoag's object, about 600 million light-years away, is a ring galaxy with a near-perfect ring of bright blue stars surrounding a yellow nucleus. Higher-resolution images from Hubble revealed even more detail, showing the ring contains star-forming regions and older stellar populations. The Antennae galaxies, about 45 million light-years away, show two spiral galaxies in the process of merging. Telescopes reveal long tidal tails of stars and gas stretching hundreds of thousands of light-years from the colliding galaxies. The collision has triggered intense star formation visible in optical, infrared, and X-ray telescopes. Different types of telescopes reveal different aspects of galaxies. Optical telescopes show stars and star-forming regions. Infrared telescopes pierce dust clouds to reveal hidden star formation. Radio telescopes detect neutral hydrogen and map galaxy rotation. X-ray telescopes show hot gas and active galactic nuclei. Each wavelength provides unique information. Galaxy colors tell us about stellar populations and star formation history. Blue galaxies contain young, hot stars and are actively forming stars. Red galaxies contain older, cooler stars and have largely shut down star formation. The transition from blue to red galaxies represents a major phase in galaxy evolution. Telescopes observing galaxies at various distances reveal when and how this transition occurred. The relationship between galaxy mass and star formation rate evolves across cosmic time. At high redshifts, corresponding to the early universe, massive galaxies form stars prolifically. Closer to us, representing later times, massive galaxies have largely stopped forming stars while smaller galaxies continue. This downsizing, where massive galaxies shut down first, emerged from telescope surveys comparing galaxies at different distances. Active galactic nuclei, powered by supermassive black holes, manifest in various forms. Quasars shine brilliantly, outshining their host galaxies. Seyfert galaxies show active nuclei, but also prominent stellar light. Radio galaxies emit powerful jets, extending millions of light-years. These different manifestations might reflect viewing angle or evolutionary stage. Telescopes observing AGN across cosmic time reveal how black hole feeding has evolved. The environments galaxies inhabit affect their evolution. Cluster galaxies, living in dense environments with hundreds or thousands of neighbors, evolve differently than field galaxies in relative isolation. Cluster galaxies experience ram pressure stripping as they plow through hot intra-cluster gas, removing their own gas and shutting down star formation. Telescopes comparing cluster and field galaxies at various distances show these environmental effects. Galaxy groups, smaller than clusters but more common, also influence galaxy evolution. The local group, containing the Milky Way, Andromeda, and about 50 smaller galaxies, exemplifies this structure. Interactions within groups can trigger star formation, drive mergers, and transform galaxy morphologies. Telescopes, studying groups across cosmic time, reveal how these intermediate environments shape galaxies. Dwarf galaxies, much smaller than giants like the Milky Way, outnumber large galaxies but are harder to study due to their faintness. The faintest known galaxies contain only a few thousand stars, barely qualifying as galaxies at all. These ultra-faint dwarfs might represent fossils from the early universe, preserving conditions from billions of years ago. Telescopes detecting them nearby reveal ancient stellar populations. Irregular galaxies, lacking the organized structures of spirals or ellipticals, are common at high redshifts. The early universe contained few well-formed spirals. Most galaxies appeared chaotic and clumpy. As the universe aged, visible in telescope observations progressing from distant to nearby, galaxies developed more regular morphologies. This transformation from irregular to regular remains an active area of research. Galactic winds driven by supernovae and active nuclei carry gas out of galaxies into the surrounding intergalactic medium. X-ray telescopes detect hot, outflowing gas. Optical spectra show absorption lines from cool gas streams. These winds enrich the intergalactic medium with heavy elements and regulate star formation by removing gas. Telescopes comparing winds at different cosmic epochs show how feedback has operated throughout cosmic history. The metallicity of galaxies, their abundance of elements heavier than helium, increases over cosmic time. Early galaxies, observed at high redshifts, contain relatively few heavy elements. Nearby galaxies show much higher metallicities, the cumulative result of billions of years of stellar nucleosynthesis. Telescopes, measuring metallicities through spectroscopy, directly trace chemical enrichment across cosmic history. Ultraluminous infrared galaxies, incredibly bright in infrared but often faint in optical light, represent periods of intense star formation or AGN activity. These galaxies form stars at rates of hundreds to thousands of solar masses per year, often during major mergers. Infrared telescopes like Spitzer detected thousands of these objects, many at high redshifts representing early cosmic epochs. Submillimeter galaxies, detected by telescopes sensitive to submillimeter wavelengths, represent dusty star-forming galaxies from cosmic noon. These galaxies are almost invisible in optical light, but shine brightly at longer wavelengths. They contribute significantly to cosmic star formation history, but were largely unknown before submillimeter telescopes revealed them. The stellar mass function, describing how many galaxies exist at each mass, evolves over cosmic time. Telescopes observing at different redshifts measure this function across billions of years. The number of massive galaxies increases with time as smaller galaxies merge and grow. This assembly history reveals how today's massive ellipticals formed from smaller progenitors. Mapping the universe requires telescopes to survey vast regions of sky, capturing light from millions of galaxies at various distances and therefore various epochs. These surveys create three-dimensional maps of cosmic structure across time. The Sloan Digital Sky Survey began operations in 2000 and used a dedicated telescope in New Mexico to photograph and measure spectra of millions of galaxies. The resulting three-dimensional map revealed the cosmic web. Galaxies distributed along filaments, connecting massive clusters, with enormous voids between. This structure assembled over billions of years, and SDSS captured it at various stages. Each galaxy in the SDSS appears from different times depending on its distance. By arranging galaxies by redshift, astronomers create slices through time. Nearby galaxies show mature structure. Distant galaxies show earlier stages of assembly. The 2-degree Field Galaxy Redshift Survey, conducted with the Anglo-Australian Telescope, measured distances to over 200,000 galaxies. This survey reached back several billion years, revealing how galaxy clustering and large-scale structure have changed. The Deep 2 Galaxy Redshift Survey targeted more distant galaxies, measuring spectra for about 50,000 galaxies between 3 and 7 billion light-years away. These observations show galaxies when the universe was roughly half its current age. Star formation was more vigorous then. Galaxies were smaller on average. Mergers were more common. The Cosmos survey used multiple telescopes, including Hubble, Spitzer, XMM Newton, and others to observe a 2-square-degree field. By combining data from telescopes sensitive to different wavelengths, Cosmos built a comprehensive view of galaxy evolution. X-ray observations revealed active galactic nuclei from billions of years ago. Infrared observations detected dusty, star-forming galaxies from when the universe was young. Optical observations measured galaxy shapes and colors across various epochs. The CANDLES survey with Hubble observed several fields, totaling about 1,000 arc-minutes, reaching to extremely distant galaxies over 12 billion light-years away. These observations captured galaxies when the universe was less than 2 billion years old. Telescopes revealed that early galaxies were smaller, more irregular, and undergoing rapid star formation. This was the era of galaxy assembly. The Hubble Deep Field revealed thousands of galaxies by staring at an apparently empty patch of sky for days. Many are over 10 billion light-years away. The Hubble Ultra-Deep Field pushed even farther, revealing galaxies from over 13 billion years ago. Some of these galaxies are among the first to form after the Big Bang. Webb has pushed the frontier even farther with its infrared capabilities. Glass Z13, one of Webb's early discoveries, might show a galaxy from only 300 million years after the Big Bang. These observations reveal what the first galaxies looked like. Webb's discoveries are rewriting our understanding of early galaxy formation. Not only are galaxies appearing earlier than expected, but they're also more massive and more structured. Some galaxies Webb has detected at high redshifts show disk structures and even spiral patterns, suggesting organized rotation developed quickly after the Big Bang. The chemical composition of early galaxies surprises astronomers. Webb's spectroscopy detects elements like oxygen, nitrogen, and carbon in galaxies only a few 100 million years after the Big Bang. This implies rapid enrichment from early generations of stars. Understanding how so many heavy elements formed so quickly challenges models of early stellar evolution. Webb's observations of galaxy mergers at high redshifts reveal how structure formed hierarchically. Small galaxies merged to form larger ones. Many high redshift galaxies show disturbed morphologies, indicating recent interactions. These mergers trigger star formation and build galactic mass. By watching mergers across cosmic time, telescopes directly observe how today's massive galaxies assembled. The epoch of reionization, when the first stars ionized the surrounding neutral hydrogen, remains partially mysterious. Webb is beginning to detect the galaxies responsible for reionization. These early galaxies, small but producing intense ultraviolet radiation, gradually ionized bubbles that expanded and merged. Webb's observations constrain when reionization completed and which types of galaxies drove it. Population 3 stars. The first stars made purely of hydrogen and helium remain undetected. These stars probably formed about 200 million years after the Big Bang. They would have been massive, hot, and short-lived. Webb might detect their signatures indirectly through their effects on surrounding gas or through direct detection if any formed later than expected. Finding population 3 stars would reveal the true beginning of stellar evolution. High redshift quasars detected by Webb and other telescopes raise questions about early black hole growth. How did supermassive black holes billions of times the Sun's mass form when the universe was less than 1 billion years old? Standard black hole growth models struggle to produce such massive black holes so quickly. Webb's observations might reveal whether these early black holes formed from massive seed black holes or grew exceptionally fast through super-Eddington accretion. Gravitational lensing by foreground galaxy clusters magnifies background galaxies, allowing telescopes to see farther than otherwise possible. Webb uses this cosmic magnification to detect galaxies too faint to see directly. Some of the most distant galaxies Webb has detected appear behind massive clusters that act as natural telescopes, boosting their brightness by factors of 10 or more. Infrared surveys excel at finding dusty galaxies whose visible light is absorbed and re-emitted at longer wavelengths. The Spitzer Space Telescope conducted several deep surveys, detecting galaxies undergoing intense star formation hidden behind dust. These observations showed that much of cosmic star formation, especially in the early universe, occurred in dusty environments invisible to optical telescopes. X-ray surveys with telescopes like Chandra and XMM Newton reveal active galactic nuclei powered by supermassive black holes. By surveying at different depths and areas, these missions mapped how black hole activity has changed over cosmic time. Gravitational lensing surveys use telescopes to measure how foreground galaxy clusters distort images of background galaxies. By analyzing thousands of galaxy shapes, astronomers map dark matter distribution. These surveys probe dark matter across cosmic history. Time domain surveys monitor how the sky changes. The Palomar Transient Factory and now the Zwicky Transient Facility repeatedly photograph large areas of sky, identifying anything that's changed. These surveys discover supernovae, variable stars, asteroids, and other transient phenomena. Automated surveys are revolutionizing astronomy. The Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, will photograph the entire visible sky every few nights once operations begin. This continuous monitoring will create a time-lapse movie of the universe. The power of automated surveys lies in their ability to detect change. Transient events like supernovae, variable stars, asteroids, and potentially hazardous near-Earth objects reveal themselves through comparison of images taken at different times. But remember that every change observed is delayed by light travel time. A supernova detected in a galaxy 1 billion light-years away shows us an explosion from 1 billion years ago. Surveys at different wavelengths complement each other. Radio surveys like VLAS, the Very Large Array Sky Survey, map the radio universe, detecting everything from star-forming galaxies to active galactic nuclei. Infrared surveys from space telescopes like Spitzer reveal dusty, star-forming galaxies invisible in optical light. X-ray surveys with Chandra and XMM Newton catalog black holes and hot gas across cosmic history. The synergy between surveys creates a comprehensive view. A galaxy might appear unremarkable in optical light, but shine brightly in infrared, revealing hidden star formation. The same galaxy might emit X-rays from an active nucleus. Radio observations might detect jets extending far beyond the visible galaxy. Each wavelength adds a piece to the puzzle, and each shows the galaxy from the past. Deep surveys targeting small areas complement wide-area surveys covering large swaths of sky. The Hubble Deep Fields, the Candel Survey, and similar efforts observe tiny patches with exquisite sensitivity, reaching the faintest, most distant galaxies. Wide surveys like SDSS observe millions of galaxies over thousands of square degrees, tracing large-scale structure. Together, they map cosmic history from multiple perspectives. Spectroscopic surveys provide redshifts for millions of galaxies, converting two-dimensional images into three-dimensional maps. These surveys reveal not just where galaxies are on the sky, but how far away they are. And therefore, when in cosmic history, we're observing them. The resulting three-dimensional maps show how structure evolved over billions of years. Future surveys will push even farther. The Roman Space Telescope will conduct wide-area infrared surveys, finding galaxies Webb might miss by targeting different regions or observing at different depths. Ground-based spectroscopic surveys with new instruments on large telescopes will measure redshifts for hundreds of millions of galaxies, creating unprecedentedly detailed three-dimensional maps. Machine learning is becoming essential for processing survey data. With billions of galaxies to classify, human inspection is impractical. Neural networks trained on galaxy images can identify morphologies, detect anomalies, and find rare objects. These algorithms must be carefully designed to avoid missing unexpected phenomena not represented in training data. The combination of deep observations, wide surveys, multi-wavelength coverage, and spectroscopic follow-up is painting a comprehensive picture of how galaxies formed and evolved. Each observation looks back in time. By combining observations at different distances, astronomers assemble a coherent history of galaxy evolution, from shortly after the Big Bang to the present. By comparing telescope observations at different distances, astronomers watch how the universe has changed over billions of years. Star formation rates have shifted dramatically. When telescopes observe nearby galaxies, they see modest star formation. The Milky Way forms stars at about 1 to 2 solar masses per year. When telescopes observe galaxies a few billion light-years away, they see higher rates. And when they observe galaxies 6 to 10 billion light-years away, they see galaxies forming stars at incredible rates, sometimes hundreds of solar masses per year. The Good survey, conducted with Hubble and many other telescopes, mapped this decline. By photographing galaxies at many different distances, the survey traced star formation from about 500 million years after the Big Bang to the present. The peak occurred about 10 billion years ago. Since then, star formation has declined steadily. Galaxy morphology has evolved too. When telescopes observe very distant galaxies, they see small, irregular, chaotic systems. These early galaxies don't have well-defined spirals or elliptical shapes. Instead, they're clumpy, with multiple bright regions of star formation. At intermediate distances, telescopes see galaxies developing more organized structures. Some have nascent spiral arms. Others are becoming more elliptical. Nearby galaxies show mature structures, grand spirals with well-defined arms, or smooth ellipticals with little star formation. Galaxy mergers shape this evolution. When telescopes survey distant regions, they see many signs of interactions. Tidal tails stretching between colliding galaxies, disturbed morphologies indicating recent mergers. Close to us, major mergers are less common, though telescopes still occasionally observe galaxies in the process of colliding. The abundance of quasars has changed over cosmic time. When telescopes survey nearby space, quasars are rare. Most supermassive black holes are quiet, but when telescopes look farther back, 6 to 10 billion light-years away, quasars become much more common. The peak era of quasar activity was about 10 to 12 billion years ago. This evolution reflects how galaxies have changed. Young galaxies had abundant gas that fell into central black holes, powering quasars. As galaxies aged, gas got consumed and quasars shut off. Chemical evolution is visible through telescope spectroscopy. When telescopes analyze light from distant galaxies, they see absorption and emission lines indicating chemical composition. Very distant galaxies contain relatively few heavy elements. Closer galaxies show progressively more heavy elements, as stellar nucleosynthesis gradually enriched the cosmic gas. Large-scale structure has evolved too. In the very early universe, visible through the most powerful telescopes, matter was distributed almost uniformly. Over time, gravity amplified tiny variations. Dense regions pulled in more matter. Voids formed as matter left under dense regions. The Sloan Digital Skies Survey used ground-based telescopes to map millions of galaxies, creating three-dimensional maps of cosmic structure. The cosmic web becomes apparent. Galaxies lying along filaments connecting large clusters with vast voids in between. This structure assembled over billions of years. The filamentary structure of the cosmic web reflects the initial density fluctuations in the early universe. Slightly overdense regions attracted more matter through gravity, forming filaments along which galaxies condensed. Underdense regions became voids, depleted as matter flowed toward denser regions. Simulations of structure formation match observations remarkably well, confirming our understanding of gravitational collapse driven by dark matter. Baryon acoustic oscillations, sound waves in the early universe left an imprint on galaxy clustering. This standard ruler, with a scale set by physics in the first few 100,000 years, appears in galaxy surveys as a preferred separation distance. Telescopes measuring this scale at different redshifts trace cosmic expansion history, providing an independent measurement of dark energy. The cosmic web evolves as the universe expands. Early observations show a finer web with shorter filaments and smaller voids. Later observations reveal longer filaments and larger voids as structures merge and grow. Comparing observations across cosmic time directly shows structure evolution in action. Redshift space distortions in galaxy surveys reveal how gravity affects galaxy motion. Galaxies don't just move with cosmic expansion, but also fall toward overdense regions and stream away from voids. These peculiar velocities distort the observed redshift distribution. By measuring these distortions, telescopes constrain the growth rate of structure, testing gravity on cosmological scales. Weak gravitational lensing surveys measure the distortion of background galaxy shapes by foreground mass. Unlike strong lensing, which produces obvious arcs and multiple images, weak lensing creates subtle elongations, requiring statistical analysis of thousands of galaxies. These surveys map dark matter distribution directly, revealing how dark matter halos have grown over cosmic time. Cosmic shear, the correlation of galaxy-shaped distortions across the sky, traces the matter distribution between us and distant galaxies. By analyzing shear at different distances, corresponding to different cosmic epochs, telescopes map how matter clustering has evolved. These observations constrain both dark matter properties and dark energy behavior. Galaxy-galaxy lensing reveals dark matter halos around individual galaxies. Background galaxies appear slightly distorted by the foreground galaxy's mass. The strength of this effect depends on the dark matter halo mass. Measuring galaxy-galaxy lensing for thousands of galaxies at various distances shows how dark matter halos have evolved. Cluster mass measurements combine multiple techniques. X-ray observations reveal hot intracluster gas. Gravitational lensing maps total mass. Galaxy dynamics measure mass from velocity dispersion. These independent measurements should agree, and generally do, confirming our understanding of cluster physics. Telescopes applying these techniques at various redshifts trace cluster mass evolution. The Sunyaev-Zeldovich effect, where CMB photons gain energy passing through hot cluster gas, provides another mass measurement technique. Radio telescopes detect the resulting spectral distortion. This effect's strength depends on cluster mass and is independent of redshift, making it valuable for finding distant clusters. SZ surveys have detected thousands of clusters across cosmic time. Dark matter's role becomes visible through gravitational lensing observations. Telescopes detect how light from distant galaxies is bent by foreground galaxy clusters. By analyzing these distortions, astronomers map dark matter distribution. The agreement between observations and simulations confirms that dark matter drove structure formation over cosmic time. Certain epochs in cosmic history mark fundamental transitions. Telescopes observing at specific distances capture light from these milestone eras. The epoch of reionization occurred roughly between 150 million and 1 billion years after the Big Bang. Before this period, the universe was dark and neutral. The first stars and galaxies then formed, emitting ultraviolet radiation that ionized surrounding hydrogen. Telescopes like Webb are beginning to observe this era. During reionization, bubbles of ionized hydrogen expanded around early galaxies, gradually merging until the entire universe became ionized. Telescopes, observing galaxies at different redshifts during this epoch, see varying degrees of ionization in the intervening intergalactic medium. Some light from these early galaxies is absorbed by neutral hydrogen along the line of sight. Later galaxies show less absorption as ionization progressed. Webb has detected galaxies from this era appearing only 200 to 300 million years after the Big Bang. These observations are revolutionizing our understanding of how quickly galaxies formed. Earlier models suggested galaxy formation should have been slower. Webb's observations show galaxies appeared earlier and grew faster than expected. Cosmic noon refers to the period about 8 to 12 billion years ago when star formation in the universe peaked. Telescopes observing this epoch see galaxies forming stars at rates 10 times higher than today. Massive galaxies were assembling rapidly. Black holes at galactic centers were actively feeding and growing. This was the universe's most productive era. The JWST Deep Extragalactic Survey targets this epoch, revealing galaxies in their prime. Infrared observations penetrate the dust that often shrouds intense star formation. Spectroscopy shows how gas was flowing into and out of galaxies, fueling star formation, while feedback from supernovae and black holes regulated growth. The transition from cosmic noon to today involved a gradual decline in star formation. Galaxies consumed or expelled their gas. Mergers became less frequent as the universe expanded and galaxies moved farther apart. Telescopes observing galaxies at intermediate distances, between 2 and 8 billion light-years, capture this transition. Star formation rates gradually decrease. Galaxy morphologies become more regular. The chaotic early universe settles into the more orderly cosmos we see nearby. Quasar evolution parallels this story. The epoch of peak quasar activity occurred around 10 to 12 billion years ago. Telescopes detect quasars shining with incredible luminosity, powered by black holes consuming vast amounts of gas. These quasars ionized and heated large regions around them, affecting galaxy formation in their vicinity. Later, quasars, observed at closer distances, are generally less luminous. By about 6 billion years ago, quasar activity had declined significantly. The most massive black holes had already formed. Gas available to feed them had been depleted. Today, quasars are rare. Most supermassive black holes are dormant. The formation of heavy elements traces another milestone. The very first stars, population 3 stars, contained only hydrogen and helium. When these stars died, their supernovae enriched the interstellar medium with the first heavy elements. Second-generation stars, population 2, contained small amounts of heavier elements. Modern stars like the Sun, population 1 stars, contain much higher abundances of heavy elements. Telescopes haven't yet directly observed population 3 stars. These first stars probably formed only a few 100 million years after the Big Bang. They would have been massive, burning hot and bright but dying quickly in supernovae. Their signature might be detected in upcoming observations by Webb or future telescopes. Chemical evolution continues today. Each generation of stars adds more heavy elements to the cosmos. Telescopes measuring stellar compositions at various distances show this progression. Ancient stars observed in our galaxy show low heavy element abundances, revealing they formed from less enriched gas. Young stars show higher abundances, evidence of billions of years of stellar nucleosynthesis. Cluster evolution represents another milestone. Galaxy clusters are the largest gravitationally bound structures in the universe. Telescopes observe mature clusters nearby, containing hundreds or thousands of galaxies. At greater distances, corresponding to earlier times, clusters appear less evolved, with more irregular shapes and higher fractions of spiral galaxies. The most distant clusters detected, over 10 billion light-years away, are still assembling. Telescopes show protoclusters, regions of enhanced galaxy density that will eventually collapse into massive clusters. These observations reveal how structure formation proceeded from small initial perturbations to the massive clusters we see today. Void evolution shows the flip side of structure formation. Cosmic voids, vast regions of space with few galaxies, have grown over time as matter streamed out of underdense regions toward overdense ones. Telescopes mapping galaxy positions at various distances show how voids have expanded. Early universe observations show smaller, less empty voids. Modern observations reveal enormous voids, hundreds of millions of light-years across. Many of astronomy's most important discoveries came from using telescopes to look back in time. Edwin Hubble's discovery of the expanding universe in 1929 came from telescope observations of galaxies at different distances. Using the Mount Wilson telescope, Hubble measured distances using Cepheid variables and measured velocities from spectral redshifts. He found that distant galaxies were moving away, and the farther away they were, the faster they receded. This meant the universe itself was expanding. The discovery of dark energy came from telescope observations of distant supernovae in 1998. Two teams independently used ground-based and space telescopes to study Type Ia supernovae billions of light-years away. These supernovae appeared dimmer than expected, indicating they were farther away than they should be if the universe's expansion had been constant or slowing. The only explanation, the expansion was accelerating. This discovery required telescopes capable of detecting supernovae in distant galaxies and measuring their properties precisely. The Hubble Space Telescope played a crucial role, confirming ground-based observations and pushing to even greater distances. The result fundamentally changed our understanding of the universe's composition and fate. Before 1998, the consensus was that the universe's expansion should be slowing due to gravity. Type Ia supernovae, used as standard candles to measure cosmic distances, were expected to appear brighter than predictions based on constant expansion. Instead, they appeared dimmer, indicating acceleration. This discovery required explaining what could drive acceleration. Dark energy, a mysterious component making up about 68% of the universe's energy density, was proposed, but we still don't know what dark energy is. Gamma-ray bursts, discovered accidentally in the 1960s, remained mysterious until telescopes could quickly observe their afterglows. In the 1990s, satellite telescopes like Beppo-Sachs detected gamma-ray bursts and immediately alerted ground-based telescopes to observe the fading afterglows. Spectroscopy showed these bursts came from extremely distant galaxies, some over 13 billion light-years away. These observations revealed that gamma-ray bursts are the most powerful explosions since the Big Bang, visible across most of the observable universe. Telescopes studying their afterglows revealed the chemical composition of gas in the early universe, providing a unique probe of cosmic history. Fast radio bursts represent a more recent mystery. These millisecond duration radio pulses were first detected in 2007. Initially, only a handful were known. Modern radio telescopes now detect them regularly. Most come from cosmological distances, billions of light-years away. The source of fast radio bursts remained controversial for years. Some proposed exotic explanations like evaporating black holes or alien signals. In 2020, telescopes detected a fast radio burst from a magnetar in our galaxy, providing crucial clues. These intensely magnetic neutron stars can produce bursts through magnetic eruptions. But the full picture of what creates fast radio bursts, especially those from distant galaxies, is still being assembled. The discovery of exoplanets surprised many astronomers with their diversity. When the first exoplanet around a sun-like star was confirmed in 1995, it orbited extremely close to its star, completing an orbit every 4 days. This hot Jupiter configuration was completely unexpected. Our solar system has no analog to such a planet. Subsequent telescope observations revealed even more surprising systems. Planets orbiting binary stars. Planets with wildly elliptical orbits. Mini-Neptunes and super-Earths, with no counterpart in our solar system. Free-floating planets ejected from their systems. These discoveries showed that our solar system is just one possible configuration among countless varieties. The rapid evolution of early galaxies observed by Webb surprised theorists. Models suggested galaxies should form gradually over hundreds of millions of years. Webb's observations showed large, luminous galaxies existing only 200 to 300 million years after the Big Bang. These galaxies appear more massive and mature than models predicted. This discovery is forcing revisions to galaxy formation theories. Perhaps the first stars formed earlier than thought. Maybe early black holes grew faster than expected. Or perhaps dark matter properties differ slightly from current models. The discovery of the cosmic microwave background in 1964 by Penzias and Wilson used a radio telescope to detect faint microwave radiation from all directions. This background is light from 380,000 years after the Big Bang. Later, satellites like COBE, WMAP, and Planck used space-based microwave telescopes to map this radiation in exquisite detail. The tiny variations they detected are the seeds of all cosmic structure. Gravitational waves detected by LIGO provide another form of looking into the past. When LIGO detected gravitational waves in September 2015, it observed the merger of two black holes from about 1.3 billion years ago. This telescope doesn't use light, but it still reveals the past. In August 2017, LIGO detected gravitational waves from colliding neutron stars. Within seconds, telescopes around the world pointed at the location. Optical telescopes detected a new point of light. Infrared telescopes watched it fade. X-ray telescopes detected emission days later. This multi-messenger astronomy, combining gravitational wave observations with electromagnetic telescopes, revealed that neutron star mergers create heavy elements like gold and platinum. The discovery of dark matter came from telescopes observing galaxy rotation. Vera Rubin and Kent Ford used telescopes to measure how fast stars in spiral galaxies were moving at various distances from the galactic center. They found stars far from the center were moving much faster than expected, revealing the presence of invisible dark matter. Gravitational lensing observations with telescopes provided additional evidence. The Hubble Space Telescope photographed numerous examples of strong lensing, where massive galaxy clusters bend light from background galaxies, creating multiple images or arcs. These observations map dark matter distribution and confirm its existence. The measurement of the universe's age relied on telescopes observing the oldest stars. By measuring distances to globular clusters and determining the ages of their stars, astronomers established that the universe must be at least as old as its oldest stars. Combined with measurements of the expansion rate from distant supernovae and the cosmic microwave background, telescopes help determine the universe is 13.8 billion years old. The cosmic microwave background deserves deeper exploration because it represents the ultimate destination for electromagnetic telescopes looking into the past. This faint radiation tells us about the universe when it was just 380,000 years old. The CMB was predicted by George Gamow and colleagues in the 1940s as a consequence of the Big Bang theory. If the universe began in a hot, dense state and has been expanding and cooling ever since, there should be leftover radiation from when the universe first became transparent. This radiation would have been shifted to microwave wavelengths by cosmic expansion. Arno Penzias and Robert Wilson accidentally discovered this radiation in 1964 while testing a sensitive radio telescope at Bell Labs. They detected a persistent background noise coming from all directions equally. After ruling out all possible sources of interference, including pigeon droppings on their antenna, they realized they'd detected the predicted cosmic background. The temperature of the CMB is about 2.725 degrees above absolute zero. This matches predictions from Big Bang cosmology. The remarkable uniformity of this temperature across the entire sky shows the early universe was extremely smooth, with density varying by only about 1 part in 100,000. The COBE satellite, launched in 1989, made the first detailed measurements of the CMB temperature across the sky. COBE confirmed the prediction that the CMB has a perfect blackbody spectrum, exactly what's expected from thermal radiation. More importantly, COBE detected tiny temperature variations, called anisotropies, in the CMB. These variations are crucial because they're the seeds from which all cosmic structure grew. Regions slightly denser than average in the early universe had slightly higher temperatures. Regions slightly less dense had slightly lower temperatures. Over billions of years, gravity amplified these tiny differences. Dense regions attracted more matter and eventually formed galaxy clusters. Underdense regions became voids. The pattern of variations COBE detected is directly related to the distribution of galaxies we see today. The WMAP satellite, launched in 2001, mapped these variations in far greater detail. WMAP operated for 9 years, measuring the CMB temperature at millions of points across the sky. The resulting maps showed patterns at various angular scales, revealing information about the universe's composition, geometry, and age. From WMAP data, astronomers determined the universe is flat, meaning its overall geometry is Euclidean. They measured the universe's age as 13.77 billion years, with an uncertainty of only about 1%. They determined that ordinary matter makes up about 5% of the universe's total energy density, dark matter about 26%, and dark energy about 69%. These measurements transformed cosmology from a field with order of magnitude uncertainties to a precision science. The cosmic microwave background provides a snapshot of the universe at a specific moment, 380,000 years after the Big Bang. By analyzing this snapshot in exquisite detail, cosmologists constrain models of what came before and what happened after. The tiny temperature variations encode information about sound waves in the primordial plasma, the density of different matter components, and even hints about the inflationary epoch that might have preceded the Big Bang. The Planck satellite, launched in 2009, pushed CMB measurements to their practical limit for single-dish telescopes. Planck's maps revealed even finer details in the temperature variations. Planck also detected subtle polarization patterns in the CMB, providing additional information about conditions in the early universe. Polarization occurs because CMB photons scattered off electrons just before the universe became transparent. The pattern of polarization contains information about how matter was moving at that time. Large-scale patterns called E-modes have been detected and match predictions. Smaller-scale B-mode patterns, which would indicate gravitational waves from cosmic inflation, have been harder to detect due to contamination from galactic foreground emission. The acoustic peaks in the CMB power spectrum reveal particularly important information. Before the universe became transparent, sound waves propagated through the hot plasma. Regions of compression and rarefaction set up a specific pattern of density variations. When the universe became transparent, this pattern was frozen into the CMB. Telescopes measuring this pattern today see the imprint of sound waves from 380,000 years after the Big Bang. The positions and heights of these acoustic peaks depend on cosmic parameters like the universe's density, the nature of dark matter, and the properties of dark energy. By measuring these peaks precisely, CMB telescopes constrain these parameters. The agreement between CMB observations and other independent measurements, like those from type Ia supernovae, strengthens confidence in our cosmological model. The CMB also reveals information about the epoch of reionization. When the first stars and galaxies formed, their ultraviolet radiation ionized surrounding hydrogen. This reionization scattered some CMB photons, slightly affecting the patterns we observe. By analyzing this effect, telescopes studying the CMB provide constraints on when the first stars formed, complementing direct observations of early galaxies by infrared telescopes like Webb. Future CMB telescopes will search for primordial gravitational waves from cosmic inflation. These waves would leave a distinctive B-mode pattern in CMB polarization. Detecting this signal requires extremely sensitive telescopes and careful subtraction of foreground contamination from our galaxy. Several ground-based and planned space missions are pursuing this goal, attempting to look back to the universe's first fraction of a second by studying radiation from 380,000 years later. One of the most profound applications of telescope observations involves searching for life beyond Earth. Every observation of a potentially habitable world shows us that world from the past. The discovery of exoplanets transformed the search for extraterrestrial life. Before 1995, we knew of no planets outside our solar system. Now, telescopes have confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. Many orbit in their star's habitable zone where liquid water could exist on the surface. Telescopes can detect atmospheric biosignatures through transit spectroscopy. When a planet passes in front of its star, some starlight filters through the planet's atmosphere. Molecules in the atmosphere absorb specific wavelengths. By analyzing which wavelengths are absorbed, telescopes determine atmospheric composition. Oxygen, methane, and certain combinations of gases could indicate biological activity. Webb is beginning to analyze exoplanet atmospheres in unprecedented detail. Webb has detected water vapor, carbon dioxide, and other molecules in the atmospheres of several hot Jupiters. These gas giants aren't habitable, but they're easier to study because they're large and hot. The same techniques will eventually be applied to smaller, cooler planets more likely to harbor life. The transit method, used by missions like Kepler and TESS, detects planets by measuring the tiny dip in starlight when a planet passes in front of its star. This technique has revealed that planets are extremely common. Most stars have planets. Many have multiple planets. The diversity is staggering. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths with no analog in our solar system, ice giants, rocky worlds, and everything in between. The radial velocity method detects planets through their gravitational tug on their host stars. As a planet orbits, it causes the star to wobble slightly. Spectrographs detect this wobble through tiny Doppler shifts in the star's light. This method revealed the first exoplanets and continues finding planets today, especially massive ones in close orbits. Direct imaging, though challenging, has successfully photographed a few dozen exoplanets. These are typically young, hot, massive planets orbiting far from their stars. As telescopes and adaptive optics systems improve, direct imaging will detect more and smaller planets. Future missions might photograph Earth-like worlds, capturing images of potentially inhabited planets from years or decades in their past. If Webb or future telescopes detect oxygen and methane together in a rocky planet's atmosphere orbiting in the habitable zone, that would be compelling evidence for life. On Earth, oxygen is produced by photosynthesis and would quickly disappear without constant replenishment by life. Methane is also produced by life and destroyed by atmospheric chemistry. Their simultaneous presence suggests ongoing biological activity, but we would be observing that life from years or decades ago. A planet 100 light-years away, showing biosignatures today, means life existed there 100 years ago. By the time we detect it, analyze it, and perhaps attempt to communicate, centuries could pass. Any response would take centuries more to return. This is observation across vast temporal gulfs. The search for extraterrestrial intelligence extends this concept further. SETI uses radio telescopes to scan the sky for artificial signals. Any detection would represent a message from the past. A signal from 1,000 light-years away would show us alien technology from 1,000 years ago, around the time castles were being built in medieval Europe. If we detect an alien signal, we face profound questions. Did that civilization survive? Are they still transmitting? By the time our reply arrives, will anyone be there to receive it? Communication across interstellar distances is fundamentally historical. We're not conversing with aliens. We're reading their ancient messages and sending replies to their distant future. Technosignatures represent potential ways to detect advanced civilizations through telescopes. These might include atmospheric pollutants, indicating industrial processes, megastructures around stars, or waste heat from large-scale energy use. All would be historical observations. A civilization 1 million light-years away, detected through unusual absorption patterns around their star, shows us their technology from 1 million years ago. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy. One factor in this equation is the lifetime of civilizations. How long do they survive? Telescope observations can only detect civilizations that existed at the right time for their signals to reach us now. Civilizations that rose and fell millions of years ago remain invisible unless they left permanent artifacts. Panspermia. The idea that life might spread between worlds also involves time travel effects. If microorganisms can survive in space and seed new worlds, the life we might detect on a distant planet could have originated elsewhere millions of years ago. Telescopes observing biosignatures would reveal life's descendants, evolved over eons from their original source. The habitable zone around a star changes as the star evolves. Early in a star's life, the habitable zone is closer. As the star ages and brightens, the habitable zone moves outward. Telescopes observing stars at various ages see habitable zones at different distances. A planet might be habitable for billions of years, then become too hot, or start cold and warm into habitability. Observations capture single moments in these long histories. Future telescopes might directly image Earth-like planets around nearby stars. The proposed Habitable Worlds Observatory would photograph rocky planets in habitable zones and analyze their atmospheres. If it images a planet 30 light-years away showing biosignatures, we're seeing alien life from 30 years ago. The organisms creating those biosignatures have lived, reproduced, and perhaps died in the decades since that light left. The prospect of finding life through telescope observations raises philosophical questions. We would be watching life from the past, unable to interact in real time. If that life is intelligent, we can't have conversations. If it's microbial, we can only observe its cumulative effects on atmospheric chemistry. When a supernova explodes, astronomers immediately search archived telescope images of that region. These archives might show the progenitor star before it exploded, revealing what type of star produces what type of explosion. Variable star monitoring by telescopes relies on comparing observations separated by decades or centuries. Long-term monitoring reveals slow changes over periods longer than human lifetimes. Historical telescope observations, combined with modern data, provide baselines spanning centuries. Does a Cepheid's pulsation period change over decades or centuries? How does Mira's pulsation amplitude vary? These questions require comparing observations separated by a century or more. Exoplanet transit timing with precise telescope photometry detects additional planets through gravitational effects. When one planet transits, others in the system gravitationally perturb its orbit, slightly changing transit times. Telescopes detect these tiny timing variations, revealing hidden planets. Multi-messenger astronomy combines telescope observations at different wavelengths with gravitational wave detections. When neutron stars collide, gravitational wave telescopes detect the merger. Within seconds, electromagnetic telescopes worldwide observe the same event at all wavelengths. This coordination reveals far more than any single observation. Gravitational time delays, measured by telescopes, provide independent measurements of cosmic expansion. When a quasar is gravitationally lensed by a foreground galaxy, creating multiple images, brightness variations appear in the different images at different times. Telescopes measure these delays, determining the expansion rate. Stellar archaeology uses telescopes to study old stars in our galaxy. These stars formed billions of years ago from gas enriched by only a few generations of earlier stars. Telescope spectroscopy reveals their compositions, telling us about the early Milky Way. Pulsar timing with radio telescopes provides incredibly precise tests of physics. By monitoring pulsar pulses over years, telescopes detect tiny variations from orbital motion, gravitational waves, and other effects. The regularity of pulsar pulses rivals atomic clocks. Some millisecond pulsars spin hundreds of times per second with incredible stability. By timing these pulses precisely over years, astronomers detect minute changes that reveal physical processes. A pulsar in a binary system shows periodic variations as it orbits its companion. The orbit itself slowly decays as the system emits gravitational waves, exactly as Einstein's general relativity predicts. Pulsar timing arrays, networks of telescopes monitoring multiple pulsars simultaneously, search for gravitational waves from supermassive black hole binaries. As gravitational waves pass through the galaxy, they slightly stretch and compress space, causing correlated timing variations in pulsars across the sky. Detecting this signature would reveal merging black holes billions of light years away. Asteroid tracking represents another practical application. Telescopes survey the sky for near-Earth asteroids that might pose collision threats. When a new asteroid is discovered, follow-up observations determine its orbit. But orbital calculations must account for light travel time. An asteroid observed now appears where it was minutes or seconds ago. Precise predictions require corrections for this delay. Microlensing surveys use telescopes to detect planets around distant stars through gravitational lensing. When a star passes in front of a more distant background star, its gravity acts as a lens, temporarily brightening the background star. If the foreground star has planets, they create additional brief brightening events. These surveys require monitoring millions of stars, comparing images separated by hours or days. Occultations provide another technique. When an asteroid or moon passes in front of a distant star, telescopes along the path of the shadow observe the star wink out briefly. Timing these occultations from multiple locations reveals the object's size and shape. Historical occultation observations, some going back decades, help refine orbital models. Binary star observations using interferometry push the limits of angular resolution. When two stars orbit close together, even large telescopes struggle to resolve them separately. Interferometry combines light from multiple telescopes, achieving resolution equivalent to a telescope as large as the separation between them. These observations reveal binary orbits in exquisite detail, determining stellar masses with high precision. Astrometry, precise measurement of stellar positions, reveals unseen companions through their gravitational influence. A star with an orbiting planet wobbles slightly as both orbit their common center of mass. Telescopes measuring positions over years detect this wobble. The Gaia Space Telescope's precision astrometry has revealed thousands of binary stars and promises to detect thousands of exoplanets. Proper motion measurements track how stars move across the sky over years or decades. Most stars move slowly enough that motion is only detectable by comparing observations separated by years. Barnard's star, about 6 light-years away, has the highest known proper motion, crossing the width of the full moon in about 180 years. Historical telescopic observations extending back over a century provide the baseline for measuring these motions. Photometric monitoring of stars reveals variability on timescales from minutes to decades. Some stars vary regularly, pulsating or being eclipsed by companions. Others vary irregularly, experiencing flares or eruptions. Long-term photometric monitoring requires comparing observations across years or decades, watching how stellar brightness evolves. The American Association of Variable Star Observers maintains a database of observations extending back over a century. Amateur and professional observers contribute measurements, creating baselines spanning human lifetimes. These observations reveal slow changes in variable stars that wouldn't be apparent from short-term monitoring. Space weather monitoring uses telescopes observing the Sun and solar system planets. Solar flares and coronal mass ejections affect Earth's magnetosphere and can damage satellites. Telescopes monitoring the Sun provide warning of events that will reach Earth in hours or days. But even sunlight takes 8 minutes to reach Earth, so solar observations always show the Sun from 8 minutes ago. Cometary observations with telescopes track these icy visitors from the outer solar system. As comets approach the Sun, they develop tails of gas and dust. Telescopes monitoring comets over weeks or months watch how tails evolve. Historical observations of periodic comets like Halley's Comet, appearing every 76 years, extend back centuries and help refine orbital predictions. These practical applications all rely on telescopes' fundamental capability, gathering photons that have traveled across space, revealing phenomena from the past. From cataloging stellar evolution to detecting exoplanets to testing fundamental physics, the finite speed of light enables unique observational methods. Future telescopes will push the boundaries, looking deeper into the past and revealing earlier chapters of cosmic history. Webb is just beginning its mission. Over the coming decade, it will detect and study galaxies from the universe's first few 100 million years, revealing how the first stars and galaxies formed. Webb's infrared capabilities are crucial because the universe's expansion stretches light from distant galaxies to longer wavelengths. What left as ultraviolet or visible light arrives as infrared after traveling 13 billion years. Webb's 6.5-meter mirror and ultra-cold detectors make it the perfect telescope for this science. The extremely large telescope, under construction in Chile, will have a 39-meter mirror when completed in the late 2020s. This enormous mirror will collect about 15 times more light than any current optical telescope. The ELT will detect even fainter objects than Webb, potentially finding population 3 stars, the very first stars made purely of hydrogen and helium. The ELT will also directly image exoplanets around nearby stars. With adaptive optics correcting atmospheric distortion, it will capture pictures of planets orbiting other suns. Spectroscopy of these planets might reveal atmospheric compositions, potentially detecting biosignatures from decades ago if life exists on nearby worlds. The Giant Magellan Telescope and 30-meter telescope represent alternative approaches to extremely large telescopes. Both will achieve similar sensitivity to the ELT, observing different parts of the sky. Together, these ground-based observatories will complement Webb's space-based observations. The Nancy Grace Roman Space Telescope, launching in the mid-2020s, will have a field of view 100 times larger than Hubble's. This wide field makes Roman perfect for surveys, finding thousands of distant galaxies and mapping cosmic structure across billions of years of history. Roman will conduct weak gravitational lensing surveys, measuring how dark matter bends light from billions of background galaxies. By mapping this distortion across the sky, Roman will reveal how dark matter was distributed at various cosmic epochs, watching structure evolve through telescope observations separated by distance and time. The Habitable Worlds Observatory, planned for the 2040s, would be specifically designed to image Earth-like planets around nearby stars and analyze their atmospheres. If HWO detects biosignatures like oxygen and methane on a planet 30 light-years away, we'd be observing alien life from 30 years ago. Radio telescope arrays like the Square Kilometre Array will observe neutral hydrogen in the early universe. The SKA will detect 21 centimeter emission from hydrogen at various redshifts, mapping how gas was distributed before the first stars formed and during the epoch of reionization when early stars ionized surrounding hydrogen. These radio observations will complement Webb's infrared observations, providing a complete picture of cosmic dawn. Radio telescopes will map the hydrogen. Infrared telescopes will detect the first stars forming within that hydrogen. Together, they'll reveal how the universe transformed from a dark hydrogen-filled void to the light-filled cosmos we observe today. Gravitational wave telescopes continue improving. LIGO and Virgo have made dozens of detections. CAGRA in Japan and LIGO India will join the network, improving localization and detection rates. The Einstein telescope, proposed for underground construction in Europe, would be far more sensitive, detecting black hole mergers from across cosmic history. LISA, the Laser Interferometer Space Antenna, would launch 3 spacecraft into solar orbit, forming a triangular gravitational wave detector millions of kilometers across. LISA would detect lower frequency waves than ground-based detectors, observing supermassive black hole mergers from billions of years ago. If LISA detects primordial gravitational waves from cosmic inflation, it would reveal the universe in its first fraction of a second, far earlier than any electromagnetic telescope can observe. This would be the ultimate look into the past, observing effects from moments after creation. Neutrino telescopes might eventually detect the cosmic neutrino background. IceCube in Antarctica detects high-energy neutrinos from distant sources. Future detectors, sensitive to much lower energies, might observe neutrinos from 1 second after the Big Bang, providing another window into the very early universe beyond what electromagnetic telescopes can reach. All these future observatories are telescopes in the broad sense, instruments that collect signals from the cosmos and reveal the past, whether detecting light, gravitational waves, or neutrinos. They all exploit the finite speed of their respective messengers to look back through time. Building ever more powerful telescopes to look deeper into the past faces significant challenges. Launch constraints limit space telescope design. Webb required an extremely complex deployment sequence because it was too large to fit in any rocket fully assembled. Its mirrors folded like origami. Its sunshield the size of a tennis court, deployed through a carefully choreographed series of steps. Any failure during deployment would have ended the mission before it began. The Starship rocket being developed might enable much larger space telescopes. With a payload faring nearly 30 meters tall and 9 meters wide, Starship could launch telescope mirrors 10 or more meters across without folding. This would simplify design, reduce risk, and potentially lower costs. But the rocket must first prove reliable enough to carry billion-dollar payloads. Funding remains a perpetual challenge. The extremely large telescope costs about 1.3 billion euros. Webb cost nearly $10 billion over its development. The next generation of space telescopes could cost even more. Governments must be convinced that scientific returns justify these investments, competing against other priorities. Light pollution increasingly threatens ground-based astronomy. As human population grows and urbanization spreads, dark sites become rarer. Low Earth orbit satellite constellations add reflected light that appears in long exposure images. Future ground-based telescopes will need sophisticated algorithms to remove satellite trails from data, or must be built in increasingly remote locations. Data volume from future surveys will be staggering. The Vera C. Rubin Observatory will generate about 20 terabytes of data per night. Processing this flood of information requires massive computing infrastructure and sophisticated algorithms. Machine learning is becoming essential for identifying interesting objects in these vast datasets. The challenge is developing AI systems that don't miss unexpected phenomena because they weren't trained to recognize them. Calibration complexity increases with telescope power. Understanding exactly how a telescope transforms incoming light into recorded data requires careful calibration. For space telescopes, this must be done remotely and maintained over decades without physical access. Small calibration errors can lead to incorrect conclusions about objects billions of light-years away. Webb underwent 6 months of commissioning after launch, carefully calibrating its instruments and aligning its mirror segments. Atmospheric absorption limits, which wavelengths ground-based telescopes can observe. Water vapor absorbs much of the infrared spectrum. Oxygen absorbs ultraviolet light. Observing at these wavelengths requires space telescopes or very high-altitude sites. Mauna Kea in Hawaii and the Atacama Desert in Chile host major observatories, partly because their high, dry conditions minimize atmospheric absorption. Technology development takes decades. Planning for major telescopes begins 20 to 30 years before first light. Technologies that seem promising might not mature in time. Engineers must predict what will be possible decades in the future and design around current limitations. This long timeline makes major observatories risky investments. Components must work reliably for years or decades, often in harsh environments. Political and economic instability can threaten projects spanning decades. Changes in government, budget priorities, or international relationships might cancel or delay telescope construction. The superconducting supercollider was cancelled despite billions already spent. While less expensive, telescope projects face similar risks if political support wanes. International partnerships spread risk but require sustained commitment from multiple nations. Environmental concerns increasingly affect telescope construction. Building observatories on pristine mountain peaks faces opposition from indigenous groups and environmental advocates. The 30-meter telescope project faced prolonged delays due to protests on Mauna Kea. Future telescope sites must balance scientific benefits against cultural and environmental impacts. Satellite megaconstellations pose growing threats to astronomy. Companies are launching thousands of satellites into low Earth orbit to provide global internet coverage. These satellites reflect sunlight, creating bright streaks across telescope images. During twilight hours, satellites can outnumber visible stars. Astronomers are working with satellite operators to minimize impact, but the problem will worsen as more satellites launch. Space debris threatens both telescopes and satellites. Defunct satellites, spent rocket stages, and collision fragments create a hazardous environment in Earth orbit. A collision with even a small piece of debris could destroy an expensive space telescope. The problem is self-perpetuating. Collisions create more debris, increasing future collision risks. This Kessler syndrome could eventually make certain orbits too dangerous to use. Funding models for astronomy are evolving. Traditional government funding faces competition from private sources. Billionaire philanthropists are funding telescope construction and operations. While this provides new opportunities, it also raises questions about priorities and access. Should privately funded telescopes focus on projects maximizing public benefit or donor interests? The search for dark matter and dark energy drives much telescope development. These mysterious components make up 95% of the universe's total energy density, yet we don't know what they are. Future telescopes will map dark matter through gravitational lensing surveys, measure dark energy through observations of distant supernovae and galaxy clustering, and search for dark matter particles through indirect detection methods. Solving these mysteries might require entirely new types of telescopes. Quantum technologies might revolutionize future telescopes. Quantum sensors could achieve sensitivities impossible with classical detectors. Quantum communication might enable ultra-secure transmission of telescope data. Quantum computing could process enormous datasets faster than classical computers. These technologies are still developing, but they might transform telescopes in coming decades. Adaptive optics continues advancing. Current systems correct atmospheric distortion across small fields of view. Next-generation systems will correct larger fields, enabling wide-area imaging at maximum resolution. Multi-conjugate adaptive optics, correcting for turbulence at multiple atmospheric layers, will push ground-based telescopes closer to the diffraction limit across wide fields. The ultimate limit for ground-based optical telescopes might be reached within decades. Mirrors larger than about 40 meters face diminishing returns as costs escalate faster than light-gathering power increases. Beyond this size, space telescopes or entirely new approaches like space-based interferometers might be needed to make further progress. Interferometry in space could achieve extraordinary resolution. Multiple spacecraft flying in formation could act as a telescope thousands of kilometers across, resolving details impossible with any single mirror. The technical challenges are immense, requiring precise formation, flying, and picometer-level control of optical paths. But the potential scientific returns are enormous. Such space interferometers could directly image Earth-sized exoplanets around nearby stars, resolving continents and oceans if they exist. They could probe the environments around supermassive black holes with unprecedented detail. They could detect faint companions to nearby stars that current instruments miss. The technology doesn't exist yet, but proposals like the Planet Formation Imager envision arrays of spacecraft working together to achieve angular resolution measured in micro-arcseconds. Free-flying space telescopes also offer flexibility. Unlike the Hubble or Webb, which are single large instruments, a constellation of smaller telescopes could reconfigure for different observing modes. They could spread apart for long baseline interferometry or cluster together for different purposes. They could be serviced, upgraded, or replaced individually rather than requiring a complete mission replacement. Lunar telescopes represent another frontier. The far side of the Moon, perpetually shielded from Earth's radio noise, would be ideal for radio astronomy. A radio telescope there could observe wavelengths blocked by Earth's ionosphere. The lunar surface provides a stable platform without atmospheric interference. Several proposals envision robots constructing telescopes from lunar materials, though such missions remain decades away. Let's step back and consider what this means. The telescope doesn't transport you through time, but it does something just as remarkable. It shows you the past directly. This capability has transformed astronomy from speculation into historical science. We don't theorize about how galaxies evolved. We observe them at different distances, different times, and watch evolution happen. We don't wonder what the early universe looked like. We point telescopes at the most distant objects and see the early universe directly. Telescopes have revealed that the universe has a history. It began in the Big Bang. The first stars formed a few 100 million years later. Galaxies assembled over billions of years. Star formation peaked about 10 billion years ago and has declined since. The universe's expansion, initially slowing, began accelerating about 5 billion years ago due to dark energy. All of this history is still accessible through telescopes because the past isn't gone. It's preserved in light traveling through space. Ancient photons from distant galaxies carry information about conditions billions of years ago. Telescopes intercept these photons and decode their message. This perspective has practical implications for how we think about cosmic communication. If we detect a signal from an alien civilization through radio telescopes, that signal comes from years or centuries ago. Any reply takes the same time to reach them. Conversations across light years aren't conversations in any normal sense. They're exchanges of messages across vast gulfs of time. It affects how we search for extraterrestrial intelligence. SETI uses radio telescopes to scan the sky for signals. Any detection would be from the past. A signal from 100 light-years away comes from 100 years ago. By the time we receive it, send a reply. And they receive our reply, 200 years have passed. Let's step back and consider what this means. The telescope doesn't transport you through time, but it does something just as remarkable. It shows you the past directly. This capability has transformed astronomy from speculation into historical science. We don't theorize about how galaxies evolved. We observe them at different distances, different times, and watch evolution happen. We don't wonder what the early universe looked like. We point telescopes at the most distant objects and see the early universe directly. Telescopes have revealed that the universe has a history. It began in the Big Bang. The first stars formed a few 100 million years later. Galaxies assembled over billions of years. Star formation peaked about 10 billion years ago and has declined since. The universe's expansion, initially slowing, began accelerating about 5 billion years ago due to dark energy. All of this history is still accessible through telescopes because the past isn't gone. It's preserved in light traveling through space. Ancient photons from distant galaxies carry information about conditions billions of years ago. Telescopes intercept these photons and decode their message. This perspective has practical implications for how we think about cosmic communication. If we detect a signal from an alien civilization through radio telescopes, that signal comes from years or centuries ago. Any reply takes the same time to reach them. Conversations across light years aren't conversations in any normal sense. They're exchanges of messages across vast gulfs of time. It affects how we search for extraterrestrial intelligence. SETI uses radio telescopes to scan the sky for signals. Any detection would be from the past. A signal from 100 light-years away comes from 100 years ago. By the time we receive it, send a reply, and they receive our reply, 200 years have passed. The philosophical implications run deep. Our entire experience of the universe beyond our immediate vicinity is historical. We never see distant objects as they are. We only see them as they were. The present moment for distant objects is fundamentally inaccessible to observation. This relates to the nature of time and causality. Events here can't instantly affect distant locations because information can't travel faster than light. The universe is structured such that distant regions are causally disconnected on short timescales. Yet there's connection through light. Photons link us to distant objects across space and time. For those of us who use telescopes, This perspective is humbling and empowering. We're using instruments built from atoms forged in ancient stars to observe other stars light years away. We're using consciousness that emerged from billions of years of evolution to contemplate cosmic history, stretching back to the beginning. Telescopes reveal that we're connected to this history. The atoms in our bodies were created in stars that died before the sun formed. We're made of stardust, looking through telescopes at other stars, understanding our cosmic origins. The implications extend beyond science into philosophy and culture. The realization that we're observing the past fundamentally changes how we think about the universe and our place in it. When ancient people looked at stars, they saw eternal, unchanging lights. We now know those lights show us history, that stars are born, live, and die, that the universe itself has evolved. The implications extend beyond science into philosophy and culture. The realization that we're observing the past fundamentally changes how we think about the universe and our place in it. When ancient people looked at stars, they saw eternal, unchanging lights fixed on a celestial sphere. We now know those lights show us history, that stars are born, live, and die. That the universe itself has evolved from a hot, dense beginning through distinct phases to its current state. This perspective affects astronomy education profoundly. Students learning about the Andromeda Galaxy aren't just learning about a distant object. They're learning that they can never see it as it is now from our reference frame, only as it was millions of years ago. This introduces fundamental concepts about relativity, causality, and the nature of observation itself. The universe doesn't have a single now across vast distances. Each observation captures a specific moment from the object's past, creating a personal, historical record for each observer. This knowledge comes entirely from observing the past through telescopes. Without this capability, we couldn't have discovered the universe's expansion, its finite age, or its evolution from a hot, dense beginning to today's structured cosmos. The humility comes from realizing our insignificance in cosmic time and space. The universe existed for over 13 billion years before Earth formed. It will continue for trillions of years after our sun dies. Our entire civilization's history spans a tiny fraction of cosmic time, barely a flicker. The distances between stars and galaxies dwarf anything in human experience. Yet there's empowerment too. Despite our cosmic insignificance, we've figured out how to observe across vast stretches of time. We've built instruments that capture photons from the universe's beginning. We've decoded messages written in starlight. We understand, at least partially, where we came from and where we're going. This understanding came through patient observation and careful reasoning. Generations of astronomers built on each other's work. Galileo observed Jupiter's moons. Römer deduced light's finite speed. Hubble discovered cosmic expansion. Penzias and Wilson detected the cosmic microwave background. Each discovery built on previous observations, each looking farther back in time. The future promises even more. Telescopes not yet built will look deeper into the past, revealing earlier epochs. Perhaps we'll observe the very first stars. Maybe we'll detect signals from alien civilizations. We might discover entirely unexpected phenomena because we've learned to look at different wavelengths or in new ways. But the fundamental principle remains. Every telescope reveals the past. Light's finite speed transforms every observation into historical documentation. The universe preserves its history in light, and telescopes let us access that archive. This has practical implications beyond pure science. Understanding cosmic history helps us understand Earth's place in it. We know the elements in our bodies were created in stars. We know Earth formed from material enriched by earlier stellar generations. We know life evolved over billions of years under a sun that will eventually die. This cosmic perspective informs how we think about our planet and our future. The search for life elsewhere in the universe depends entirely on this observational delay. When we detect biosignatures on an exoplanet, we're finding evidence of life from years or decades prior. Any communication with alien civilizations would occur across vast temporal gulfs. Education and public outreach benefit from understanding telescopes as instruments that reveal history. Showing people Hubble or Webb images isn't just showing pretty pictures. It's showing actual views of the past, frozen moments from billions of years ago, preserved in photons that have journeyed across the cosmos. This visceral connection to cosmic history inspires wonder and curiosity, helping people understand their place in the universe's grand narrative. The philosophical implications continue unfolding as our observations reach deeper into cosmic history. If the present moment for distant objects is inaccessible to us, what does that mean for the nature of reality and observation? How do we think about causality across cosmic distances? These questions bridge science and philosophy, enriching both disciplines. In the end, telescopes do more than enlarge our view of the universe. They give us a view through time, revealing the universe's history directly. Every photon captured is a messenger from the past. Every observation is an act of historical documentation. Every telescope is a window not just into space, but into yesterday. When you look through a telescope, you're doing something remarkable. You're gathering photons that have journeyed for seconds, years, or eons. You're participating in humanity's ongoing effort to understand where we came from and how the universe evolved. The finite speed of light isn't a limitation, it's a gift. It transforms every telescope into a window through time, giving us access to cosmic history that would otherwise be lost. So, the next time you look through a telescope, remember those photons have been traveling to reach your eye or camera. You're witnessing history unfold. And that's one of the most extraordinary things about telescopes. They don't just magnify distant objects, they show us the past. Every observation is a journey backward through time. We're fortunate to live in an era where we can build instruments to intercept photons from across the cosmos and decode their messages. We're privileged to be conscious beings who can understand what we're seeing, who can contemplate cosmic history, who can trace our origins back to the beginning. Thank you for joining me on this journey through space and time. If you found this valuable, please like and subscribe. It helps me continue making these explorations of the cosmos. And remember, every time you look through a telescope, you're witnessing the universe's history unfolding, seeing light that has traveled across unimaginable distances and durations to reach you. Good night. And may you never look through a telescope the same way again.